Hello everyone, this is Greg from ChemCore. In this video, we're going to be talking about the worksheet about Newman projections. Now, Newman projections is definitely a very tricky concept. It is probably one of my heftier topic videos, but just because I squeezed a lot of the concept about Newman projections from drawing them and understanding them to understanding the relationships between them in terms of energy and strain into one video. Just because I feel like it made more sense just to talk about it together. If you're not comfortable with these concepts yet, or you haven't seen the topic video about it, I suggest you go watch that. It is linked in the description below. And if you haven't seen the worksheet yet, or the answer key, it is also linked in the description below, available for absolutely free on my website. And so the first couple questions we're going to be talking about is going to be comparing existing Newman projections that we have been given, and then comparing the energy level and the strain and the stability of these conformations. And so remember that depending on how we are drawing the Newman projection, it'll actually affect how stable our molecule is. And so I want you to realize that in one, we have our two methyls, or four methyls if you consider this one, then the back carbon, and then the front carbon, right? We have our four carbons, so this conformation is drawn correctly, but this is our gauche conformation. And it is called gauche because we have our two largest groups, our methyls, not completely covering each other, but next to each other. So it's not super unstable, but it's definitely not the most stable that we can get. In question 2, again, this is a valid Newman projection, but notice that we have all of our groups are just lined up right over each other, right? And so because they're lined over each other, they're going to be bumping in, especially these two methyls are going to be bumping into each other. And we call this eclipsed. Okay, or completely eclipsed because we have our largest groups completely covering each other. In question 3, however, it seems similar to our first gauche conformation, but notice that our two largest groups are actually on complete opposite sides. And so this is called our staggered conformation. And so there's not much becoming more stable than this conformation, right? There's no other way to rotate or move around these two carbons, the front and back carbon, to make this any more stable. Now, answer 4, notice that this is the same as option 1, but just flipped, right? So on the right side this time. Again, this is gauche, so it's not super unstable, but definitely not the most stable it could be. And 5 is also gauche, in which these two largest groups are still next to each other, right? Just in a different area. And so now that we have all of these labeled, notice that eclipsed is going to be your least stable. And then your staggered is going to be your most stable. And then gauche is going to be somewhere in the middle, right, between that. We actually can't compare all of these gauches. We're going to consider them as being equal to each other. But the least stable conformation out of all of these is going to be our eclipsed. And then the next question, we're actually comparing the most stable, right? So option 3 is our staggered. And so option 3 is going to be your most stable conformation. In question 3, again, we're looking for the most stable, so we're probably going to be looking for a staggered conformation. In option 1, I see these two largest groups pretty close to each other, but not completely covering each other, which means this is gauche. In option 2, we have them covering each other, which means it is eclipsed. Question 3, they're as far away from each other as possible, which means they are staggered. And then the final 2, they are both gauche. And so the most stable conformation is going to be our staggered conformation. Question 4, which conformations of 1,2-dibromoethane does not illustrate one or more gauche interactions? So we're looking for the ones that don't have gauche. So these are actually the same examples, right, as the previous question. Option 1 is gauche because we have these two groups kind of next to each other. Option 4 is also gauche. Look at these two groups next to each other. And option 5 is also gauche, because we have these two conformations next to each other, or two largest groups next to each other. And so the only two conformations that don't illustrate gauche conformations are going to be 2 and 3. And so our answer is D. In question 5, we're looking for the most stable conformation of 3-bromo 2-methylpentane from C3 to C4. And so when it comes to more complicated structures, I really do suggest to draw it out first. We have a pentane, we have a bromo on the 3, and a methyl on the 2. And so in this case, I kind of do like writing out my CH3 just because it's going to be easier to draw our conformations. Notice that we're going to be going from the C3 to C4, right? So this is our C3 and this is our C4. And C3 and C4 just really refers to the numbering. So remember your IUPAC naming, we're going to be numbering from the left side, which means this is 1, 2, 3, 4, and then 5. Meaning that on the front carbon, which is going to be C3, we're going to have a bromine. Okay, we're going to have a hydrogen, and we're also going to have this kind of larger structure, which is actually just going to be CH3 too. And then on the fourth carbon, which is our back carbon, we're going to have 2 hydrogens, right? And then we have the CH3. And so maybe it makes it easier to draw all of your groups out, right? On the fourth carbon, we're going to have both these hydrogens and then the CH3. And then on group 3, we're going to have this hydrogen, this bromine, and this larger methyl or larger hydrocarbon chain. And so we can first of all go through all our options and eliminate all the choices that don't draw this correctly. So what I notice is that in structure 5, we have this in the back, right? So this is incorrect. But all of these other structures seem technically correct, right? We have all the groups where we're supposed to have them. And since we're looking for the most stable, we can kind of start eliminating all the structures that are not going to be very stable. Okay, this is going to be eclipsed. So definitely not going to be your most stable conformation. So we can eliminate B and E. In question 3, I do see, or option 3, I do see that the front carbon and the back carbon larger groups are right next to each other. So this is going to be our Koch conformation, so also not our most stable. And in option 4, I also once again see this larger group and this larger group in the back, also right next to each other. And so we're going to call this gauche as well. But in option 1, our largest group in the front carbon and our largest group on the back carbon are as far away from each other as possible. And so we're going to call this staggered. And you can consider that bromine here is also a pretty large group, but it's nowhere as large and as kind of 3D or like spaciously demanding as this group. And so if you're comparing the largest groups, you're not really comparing based on weight, you're going to be comparing based on size, right? This is 3 carbons versus just 1 bromine. And so your largest group in the front carbon is going to be as far away as possible as the largest group on the back carbon. And so your most stable conformation should be structure 1. The most stable conformation of 2,3-dibromobutane viewed from C2 to C3. Let's take our time and draw this again. We're going to have a bromine on the 2 and a bromine on the 3. So it actually doesn't matter which you start with. You're just going to be looking at one of these directions, right? So your front carbon, right, it might help to draw out all your substituents, right? You're going to have a CH3 on each side. And so your front carbon is going to have a bromine. I'm going to move down a little bit. You're also going to have a hydrogen and a CH3. And then your back carbon, let me make this a little thicker. Your back carbon is also going to have a bromine, a hydrogen, and a CH3. Notice that I'm not really paying attention to how I'm drawing this. This is not supposed to be the most stable structure. I just want to draw it out just so we know what is going to be on our front carbon and what is going to be on our back carbon. We can easily draw the least stable conformation from this, but it gives you a good idea of what has to be where before even looking at the questions, because sometimes you'll look at something that is technically staggered, but it's, you know, it's a wrong orientation, right? We have the wrong substituents on the wrong carbons, and so that would be the wrong answer. And so looking through these options, we should make sure that all of our options have 1 carbon, 1 methyl in the front, 1 methyl in the back, 1 bromine in the front, 1 bromine in the back, which it all seems to follow pretty well. Yep, they all seem to be valid structures. So now let's look for our least stable conformations. This is going to be an eclipsed structure because we have the largest groups covering each other. So definitely not going to be our most stable structure. In structure 1, you have these larger groups covering each other. So this is going to be our gauche conformation. So also not your most stable structure. In option 4, again, you have these pretty large structures right next to each other. So again, this is another gauche conformation. And then in option 4, again, you have these pretty large groups right next to each other, bumping into each other. And so this is also one of your gauche conformations. While if you look at structure 3, we have these methyl groups as far away from each other as possible, and these bromines as far away from each other as possible. And so this is going to be your staggered conformation. In question 7, we're actually going to be looking at the same structure as we drew in the previous problem. So if you skip that problem, go back. We're looking for the conformation in which the bromines are in a gauche conformation. And the one that really shows that is going to be right over here. These bromines are right next to each other, right? So this is our gauche conformation, okay? We are also going to have, well, these bromines are completely on top of each other, so they're eclipsed. These bromines are as far away from each other as possible, so these are staggered. Although this is also gauche, these bromines are as far away from each other as possible, so they are staggered, although the conformation in total is still a gauche conformation. But in this structure, we have these bromines in a gauche conformation right next to each other. And so the only structures that we have the bromines in gauche orientation are 1 and 5, sorry. The least stable conformation of 3-bromo 2-methylpentane viewed from C3 to C4. Let's draw out our pentane. We're going to have a bromine on the 3, a methyl on the 2. And then we're looking from C3 to C4. So this is going to be our C3. This is going to be our C4. And so notice that on our C3, we're going to have the front carbon with bromine, hydrogen, and this larger group, right? Which is right over here, this big hydrocarbon group. And then on carbon 4, which is in the back, we're going to have our hydrogen, our CH3, and then our other hydrogen. I only drew one of them, but there's actually 2 hydrogens on this back carbon, right? And so, first of all, let's make sure that all of our structures correctly represent that, which I believe one of them does not, right? Structure 3 is not a correct Newman projection at all, and structure 2 also is not a correct Newman projection. So we're left with 1, 4, and 5. And if you're looking for the least stable, you're probably going to want to look at the eclipsed version of your Newman projection, because this is also always going to be your least stable conformation. And so your answer is E. In question 9 and the next question, we're actually going to be comparing the energies of our conformations. And so we're asked about what structures are at, or which conformations are at 60 degrees and 300 degrees. So if you want to consider the energy being like half as low as possible, but also kind of somewhere half as high as possible. So somewhere in the middle, right? So since it's somewhere in the middle, we're probably considering a gauche conformation, right? And so since technically we're looking at a gauche conformation, we could consider them slightly staggered, right? Since they're not on top of each other. And so we're going to consider them staggered and gauche. And in question 10, we're asked about 120 and 240, right? So this is probably one of our higher energies, right? But definitely not as high as it could be, right? So this is probably going to be our highest energy possible, so most unstable. So since it's somewhere kind of close to the top, we're probably thinking eclipsed, right? But more stable than the conformations at 0, right? So more stable than at 0 or 360. So in question 11 is where our Newman projections could get a little more complicated, is when we start involving stereochemistry. And so I'm going to try my best through the camera that you're looking at right now to illustrate or show you guys how I solve these problems. Because the way I solve these problems leaves no room for memorization, and it's literally the best way to do these problems. And I promise if you understand how I'm doing them, you will get them absolutely correct every single time. The first job is to let's number our molecule that they gave us so that we understand which one is C2 and which one is C3. So this is going to be C2 because we want to give our hydroxyl the lowest number possible, and this is going to be C3. And so if we're considering it, on the front carbon, right, we want our hydroxyl, we also want a hydrogen, and we want a CH3, okay? But unlike the previous problems where I kind of drew the substituent wherever we wanted, it's not as true anymore. Since they specify our stereochemistry by giving us wedges, it actually does matter which direction we are drawing them in. And so I want you guys to visualize that this is a flat compound on your notebook as if you're looking down right now. I know maybe my mic kind of cut out for a moment, but if this structure was literally flat on your paper, this is how you're viewing the molecule as it's drawn. What we want to do is if this is your notebook, oops, just hit my microphone. If this is your notebook and you're viewing from above by looking at a general bond line structure, what we want to do is we want to look from the side, right? From C2 to C3. And so if on a regular structure, as viewed from your notebook, let me pick up this microphone a little bit so you guys can hear me. We are looking at the hydroxyl kind of being facing up because it's on a wedge. If we were to twist our heads to the right to look from C2 to C3, our hydroxyl would end up on our right side. Now I know that my camera is flipped, right? So it might be confusing the way you're looking at me. So I urge you guys to do it along with me. If you're looking at the molecule from above, right, as if this flat bond line structure is on your paper, your wedges would always be facing up. Your dashes would be facing down, right, like this, if you can see that. So since our wedges are on top, okay, our hydroxyl is on top, if you were to twist your head like this, it would be on my right side. On my right side. This hydroxyl is now on my right side. So therefore, because of that, we need to put our hydroxyl on the right side on our Newman projection. Let me redraw that. Okay. Your hydrogen is probably going to be on your left side. Since we didn't specify, it's probably going to be on a dash. And we can draw our methyl facing up, since it kind of looks like it's facing up, right? Like kind of looks like it's looking up. Okay. Now from C3, we have this CH3 on a wedge. We have a hydrogen hanging out here, and then we have this kind of ethylene group right over here. So the first job that we really have to figure out is, well, where is going to be our methyl group? Since it's specified via a wedge, we have to actually be very specific where we put this methyl group. So again, if you have this molecule flat on your paper, like so, and you have this wedge looking up, if you were to look to your C2 to C3 side, you would have your methyl on your right side. Therefore, we draw this methyl on the right. Your hydrogen could end up on your left. And since this other ethylene group is kind of looking down, we generally are going to draw it looking down. But in general, the most important things is that your methyl over here on the back carbon is on your right, and this hydroxyl on the front carbon is on your right. And so what we can do is we can just find the option in which we have that, which is option 5. And so generally we could just switch these groups since they're not specified via stereochemistry. But in general, the way you would kind of see them in real life, since it's kind of like looking down, if you thought about it, would be drawn like that, and you wouldn't have much variability. But definitely the most important things to look at is going to be your stereochemical groups, because they're specified via wedges. So structure 5 correctly shows both our groups on the right side, but I want you guys to pay attention to one other answer choice, and that's answer choice 2. In answer choice 2, you'll actually see, I guess our orientation is mostly the same, except that it's basically completely flipped. It's almost like a mirror image in which both our groups on the CH3 on the right and our OH on the right are just flipped onto the left side, right? Do you see how these two groups are on the left, but everything else basically stayed the same? This actually would be incorrect to choose, because by saying that they're on the left, we would actually mean that they're on a dash, right? They're on a dash, and we're looking from the right. Or you can try out for yourself, right? They could be on a wedge, but we would have to look from this direction. They specified specifically looking down C2 to C3. And so because they specified the direction that we're looking at, drawing them in this direction is actually incorrect. And so the only answer choice that we can choose is choice 5. In question 12, we're going to have a similar question in which we're trying to find a staggered Newman projection for the compound that they gave us, looking from C2 to C3. So it's important to remember your IUPAC naming. We're going to start naming from the left, or numbering from the left. And so this is our C2 and this is our C3. We can also write that on our C2 we're going to have a hydrogen, and this is going to be a methyl group. I find that it helps for drawing Newman projections, just to remember what your components on each carbon is. Now, in the previous problems, like I did in the beginning of the worksheet, I actually just drew the substituents wherever I felt like it. But in this case, because they specify stereochemistry, like in the previous problem, it actually does matter where we draw them. And so chlorine is on a wedge. So if we were to draw the front carbon, it actually really does matter where we put the chlorine. I want you guys to follow the same method that I've been doing for the previous problem. I'm going to try not to hit my microphone or cover it. So if you were to look at the bond line structure, you're actually kind of looking at it from above, like this, right? But if we have this stereochemical wedge, this is actually telling us that it's looking up from our paper. So if we're going to start looking from our C2 to C3, we're going to twist our head to our left side, and that makes our wedge appear on our right. So we are going to draw our chlorine on the right. Let me make this a little longer. Okay, our methyl looks like it's kind of going down, so we're just going to draw our CH3 here. And our hydrogen seems to be going up as well. It just appears to. But this chlorine is definitely going to be the most important to identify our correct Newman projection. On the back carbon, the story is the same, right? The methyl, or similar. The methyl, again, is on a wedge. So if you were to twist your head, you would notice that our methyl appears on our right side. Okay, so this is definitely important to look out for. Our ethyl group seems to be looking down, and our hydrogen seems to be looking somewhat up, maybe left. Okay, so these groups could, I guess, be drawn differently, but this methyl and chlorine on this side must be drawn in this direction. And so if you're looking at each option, this one is not correct, this one is not correct, this one definitely isn't even the correct Newman projection, and this one is not correct. And it kind of seems like the only one that is sort of close to what we need is structure 2. The problem is that the molecule is almost like flipped. Regardless of the ethyl and the methyl group being flipped, the problem is that our chlorines and methyl group that we specifically put on the right side are now in our left. This is incorrect. I don't want you to think like, oh, maybe it's mirror, could be the same. It's incorrect. This would mean that we're looking from the other direction instead of from the C2 to C3. This would mean that we're actually looking from C3 to C2. So that would be completely a different perspective, which means our Newman projection is wrong. So actually none of these options match the bond line structure that we were given. In question 13, we're doing a similar problem, except we're looking from C3 to C4 in this structure. The most important thing first is that we number it correctly. Remember that we're going to number from our right direction because we want to give our hydroxyl the lowest number possible. So if we're looking at this carbon, we're going to have a hydrogen here, this ethyl, and this hydroxyl on a wedge. And if we're looking at this carbon, we're going to have this methyl group on a dash, our hydrogen, right, just hanging out, and we have this larger isopropyl. We'll just call this a butyl group because we kind of know that what it is. It's just a common structure, so that we don't confuse ourselves with which it is. We'll just call it Bu, right? We'll just call this Bu, and we'll call this ethyl. And so what we really have to do is we have to specifically put the groups on one of the directions. It is very important that we look at the stereochemical arrangement because they specified that this hydroxyl is on a wedge. And so if we draw this front carbon, wedges appear kind of looking up from your bond line. So if you were to flip your head, it would appear on your right side. So we would need our hydroxyl. The difference in this question from the previous two questions that we've done is we're kind of looking from the other direction. Before we were looking from this side, right? Kind of looking from this direction. But now we're looking from this direction. So you actually just are going to just twist your head into a different side. So if your bond line structure is kind of like a flat piece of paper with your wedge sticking out, this time we're going to turn to our other direction, and our wedge is now going to appear on our left side. And I'm telling you guys, like, if you were to understand the method that I'm doing, there's not a single thing that I have ever memorized for this concept. It is just this motion of twisting my head, and it all makes sense. And then our back carbon is going to be a dash. This is one of those things that we haven't really seen an example of yet, in which a dash is not going to be on top of our paper, it's actually going to be on the bottom. And so if we were to twist our heads in the same direction, looking from our right side, we would actually see our wedge on the right. And so this methyl is going to appear on our right side. This hydrogen appears to be on our left, kind of looks like it. And this Bu group will end up looking down. Now these could be kind of like drawn differently, but the most important things that we must remember is that our front hydroxyl must appear on our left and our back methyl must appear on the right. And so the only one that really fits that description is example 3. And so our answer choice should be D, only structure 3. Question 14, we're going to be looking down the C2 to C3 bond. Remember that we're going to start numbering from the right. This is going to be our C2, this is going to be our C3. And so if we were to draw this, right, we're going to have a hydrogen over here, a methyl. On carbon 3, we're also going to have a hydrogen. And we're going to have this kind of propyl group. We'll just say propyl because I don't want to write out the whole formula. If we were to look from this direction, remember we're looking from this direction, okay, we are going to have our molecule flat. Our wedge or dash is going to appear on the bottom of our molecule, and we're looking on the right side, okay? And since if we're looking on this side, my dash appears on my right hand. And so my bromine must be on my right. My methyl kind of like seems to be going down. And my hydrogen, I guess, could be going up. And on my front carbon, our chlorine is on a dash, right? And so if I twist my head again, my dash ends up on my right side. Okay, my propyl is going to probably be somewhere here. And my hydrogen is somewhere here. But definitely the most important things out of all of these substituents is that we must have our chlorine on our right side and our front bromine on our right side. And so the only structures that really show that is this. Notice that, I mean, it kind of looks different just because they, instead of drawing a peace sign on the front, they drew a Y, which is just preference, like whichever way you really prefer it. But the whole point is that bromine on the front is on the right and chlorine on the back is on the right. So the only structure that really matches our description is structure 2. And so the answer choice is D, 2 only. Question 15, which of the following is the correct Newman projection for the following compound as viewed down the indicated bond? So they're actually just drawing this for us, this little eye that I used to draw kind of like with an arrow. Realize that on this carbon we have a hydrogen pointing somewhere here probably. We have this methyl on a wedge. On the back carbon, we're going to have this methyl on a dash and this hydrogen kind of coming out somewhere. So the point is we really have to specify where this methyl and where this methyl is going to be. If we're looking from the right direction, our wedge is going to be looking up. So we kind of turn our head and our methyl ends up appearing on our left. And then we can draw our chlorine probably somewhere here, or maybe looking up actually, kind of looks more accurate. Doesn't actually matter much. And our hydrogen is going to be somewhere here. And our back carbon, we have our methyl this time on a dash. And so if we were to look from this direction, our methyl now appears on my right side. So my methyl is going to be here. Our hydrogen is probably going to be somewhere on our left, and our bromine appears like it's looking down. And so definitely the most important groups that we have to look out for is this methyl and this methyl. And so this one kind of looks more or less accurate. This one does as well. 3 is not correct. 4 is definitely not correct. And 5 also is not correct. And so we kind of narrow down that chlorine has to be on the front carbon, while in this structure, chlorine's on the back carbon. So that's an incorrect Newman projection. So our correct structure is going to be option 1. Question 16, we're doing a similar thing in which we have chlorine on a wedge. We have this methyl group, this hydrogen over here. We're going to have this methyl group on a dash. And then we're going to have a front carbon. If we look from right to left, our methyl group, or our chlorine, is looking up originally since it's on a wedge. And if we look from this direction, it now appears on our left side. So chlorine is going to be here. Our methyl is probably going to be somewhere here. And our hydrogen appears to look up. And on the back carbon, since our methyl is on a dash, it's going to be under. So if we were to look from the side, it now appears on my right side. Bromine is on a wedge, which means it should appear on my other side, right? And our chlorine is probably going to be somewhere down here. So definitely the most important groups to remember is our methyl group and bromine on the back, and our chlorine on the front. Okay, and so the only structures that really match up for that is going to be, well, this is wrong, right? This is wrong, and this is wrong. So this is somewhat looks normal. This somewhat actually does not look normal because we have this chlorine on the back carbon. And so this is correct. I want you to realize that yes, chlorine's still on our left, bromine's still on our left, and methyl is still on our right. The reason why it looks different is just because instead of drawing a peace sign like I did, they drew a Y on the front carbon, which is really just preference, right? But in general, the directionality of each of these groups is still the same and still correct. So our correct answer is D. So question 17, again, we're going to be looking at this carbon first. Chlorine's on a wedge. We have hydrogen somewhere here and methyl somewhere here. And then we have on the back carbon, just a methyl somewhere hanging out there. We're gonna have our front carbon. Since chlorine is on a wedge, it's going to be sticking out. And if we look from this direction, it appears on my left side, right? And so our methyl is probably going to be somewhere looking up, hydrogen looking down. And on our back carbon, if we're looking from our left, our fluorine is on a wedge. And so it's going to appear on our left, while our bromine is on a dash. So it's going to appear on our right. So bromine is going to be somewhere here, fluorine somewhere here, and methyl somewhere here. And so the most important groups to pay attention to is this chlorine, this fluorine, and this bromine. Okay? And so the only groups that really make sense, no, bromine's on the wrong side. This one, no, on the wrong side. This one, no, on the wrong side. This one seems correct. This one seems more or less correct. And the only thing that I really see an issue with this is that we have two bromines from somewhere, right? That's not in our structure, so that's wrong. And so the only structure that really matches up with what we drew is structure 5. Starting from question 18, we're actually going to be going the other way around. So instead of going from a bond line to a Newman, we're not going to be going from a Newman to a bond line. And so the best thing that I really suggest for you guys is to remember your directionality, right? You can eliminate a lot of questions just by understanding where your structure should be looking. So if I see these two bromines kind of on opposite sides from each other, I know that no matter which direction I look from the left side or from the right side, I know that one must be on a wedge and one must be on a dash. And so I can eliminate this structure, I can eliminate this structure, I can eliminate this structure, and I can also eliminate this structure. And so the only structure that just simply matches up with that is going to be here, right? Because we know that the bromines are on opposite sides. So one must be on a wedge, one must be on a dash. The difference of which one is which is really depends on which side we look at, whether we look from this direction or from this direction. And you guys can try it out and try to figure out which direction we're looking at. So the answer is B. In question 19, again, we're going from a Newman projection to a bond line structure. And the most important thing that I want you to realize is start from the front carbon. On the front carbon, we're going to have an ethyl group and an ethyl group in which one of them is looking at the right side, right? And then the back carbon is going to have a methyl group, another methyl group, in which one of these methyl groups is looking on the left and one of these methyl groups is looking on the right. And so what we're looking for is a structure in which we specify that one of these ethyls is either on a wedge or a dash, and on the back carbon in which one of these methyls is either the same, right? Is either the same, so either the same thing as our ethyl, or opposite, or both, right? We can specify both. And so the only structure that I really see is, well, number one, we're not specifying any of our ethyls on these two carbons, right? So this ethyl is not specified, which wouldn't really quite make sense. Structure 2, again, we're not specifying any of these ethyls on these two carbons. Structure 3 does seem that we're specifying that our ethyl is on a wedge, which could make sense, right? This is going to be our first carbon. And our back carbon, one of our methyls is also on a wedge, which would be this methyl, right? And I guess you would have to make this methyl on the opposite side. On this structure, again, yes, you're specifying where this ethyl is, but on this back carbon, you also have another ethyl, which is wrong, right? On the back, you don't have another ethyl, so that doesn't quite make sense. And on structure 5, again, your front carbon is specifying an ethyl, but your back carbon, for some reason, also has two ethyls, which doesn't exist in our Newman projection. And so this is wrong. So the only structure that really makes sense would be structure 3. Now, number 20, again, we're looking for a bond line structure. So the first thing I want you to notice is that your front carbon must have two methyls, and one of them is looking to the left. And now the back carbon, you must only have an ethyl group, right? So no other structures. So the only, if you're looking at this carbon, right, you have an ethyl on both sides, right? No matter which direction you look from, whether this direction or this direction, you're going to have this ethyl, which doesn't actually exist in our Newman projection. So we know that this is wrong. On this structure, yes, we have a methyl on the 2, right? And then on a 3, you would have an ethyl group. So that kind of makes sense, except on the front carbon, yeah, you should have two, right? So you could kind of be looking from this direction. That's definitely possible, right? On this direction, you have an ethyl. You would have to start naming from this direction. And this would be wrong, right? Because you don't have an ethyl on the front carbon. So this is a wrong structure. On structure 4, your numbering would be wrong, right? So you would be missing a methyl. So if you started from here or here, you'd only have one methyl on the front carbon. So this is wrong. And then on structure 5, if you looked at this carbon, you're missing an ethyl and you're missing a couple more carbons. So this would be wrong. So the only structure that really makes sense is structure B, or structure 2. In question 21, we're asked to draw a Newman projection for the gauche conformation of C2 to C3 bond of pentane. So one way we can do that is, let's just first draw pentane, right? Let's say this is our 2 and this is our 3. We're going to have an H and H over here. And then over here, we're also going to have H and H. So if we're looking from this direction, our front carbon must have two hydrogens. So we'll just make these two hydrogens over here. And we must have a methyl group somewhere there. But our back carbon should have, again, two hydrogens, but an ethyl group somewhere on the back. Okay? And so what we can do is, since we need to make a gauche conformation, let's put this ethyl group somewhere close to our methyl, right? Because that's the definition of a gauche conformation. And then we can put these hydrogens wherever else we want. And so there's a lot of different ways we can actually do this. Another way we can do that is, for example, just trying to have you guys understand that we're not actually specifying, since we're not given a stereochemical arrangement or wedges and dashes, we're not told what we actually have to do. This is also completely valid, right? This is still a gauche conformation and is still valid for a regular molecule of pentane. You can flip it, but the most important thing is that your front and back carbons have the right amount of things, right? And they are next to each other, which makes it gauche. In question 22, another Newman projection, we're doing 3-methylpentane. I like to actually give it CH3, and we're looking down the C2 to C3 bond, right? So on the C2, we're going to have two hydrogens. C3, we're going to have a hydrogen and then this ethyl group. So on the front carbon, what we can do is we can just put these two hydrogens left and right, and we'll put this other methyl group, this one right over here, looking up. And on this back carbon, right, now we have to pay attention for the most stable conformation. So what we really want to do is, since the biggest group on our back carbon is this ethyl group, we want to put it as far away from the biggest group on the front carbon, right? So this is going to be C2 to CH2, CH3. It's going to be as far away as possible. And then it really doesn't matter where you put this methyl group, right? Either the left or the right. Since they didn't specify wedges and dashes, we don't have to actually care. As long as these two groups, the biggest group on the front and the biggest group in the back, are looking opposite from each other, this would be the most stable conformation, or anti-staggered. This concludes the worksheet on Newman projections. I know this is not the easiest topic in organic chemistry, but I promise the more practice you put in, the easier it gets. I suggest to go over this worksheet a couple times, maybe compare your answers to me doing them in this video or the answer keys, both of which are available in the description below and on my website. And if you want to clarify some of the concepts that I've talked about in this video, go ahead and watch my topic video, which is also available on my website and in the description below. And I'll see you guys in the next video.